Yes friends, now I will explain you the next theorem of the Fourier transform. In this theorem, let fc cosine of n, nth derivative p, and f of sine nth derivative p are Fourier cosine and sine transform of the function f nth derivative x. Then first one is you have to prove f of c cosine of 2n p is equal to, this is sigma r varying from 0 to n minus 1 to the power r alpha to n minus 2r minus 1 p to the power 2r plus minus 1 to the power n p to n plus into f of c is p. And similarly the second thing you have to prove for the odd, even and odd of f of c of 2n plus 1, this one, and similarly for sine of f of s 2n for this one, and f of s 2n plus 1 of this one. That is for odd and even functions. Okay. Yes, and in this theorem also it is given that provide the first n minus 1 term of the f of x vanish as x tends to infinity, and the n minus 1th derivative as x tends to 0 is alpha n minus 1. Okay, using these we have to prove that. Okay, now we start first property. Yes, to prove this first property, yes, this one property. Yes, here we have fc, yes, fc n is equal to, according to definition we know this is 0 to infinity, yes, f nth derivative, yes, x and cos px. This is the definition of the cosine. Yes, clear? And also you know, and sine of this is, you also know, f of s nth derivative p, this can be also defined as 0 to infinity, yes, we have, yes, we know actually, yes, 0 to infinity fn x sine px dx. Yes, clear? You know these two. Okay. Now, actually, since we know that this property, or you say that since we know f of first derivative of x, this is equal to 0 to infinity, yes, minus infinity to infinity, f of x 1th, yes, e to the power I px dx. And now by parts integrating, then you get, this is f of x, integrating this first term, second term, e to the power I px minus ip and e to the power I px f of x dx. Yes, okay. Using this, okay, using this from here, let us suppose that this equation number is 1 and this equation is 2. Yes, okay. So integrating the equation number 1 using this, okay, integrating, okay, integrating equation 1, yes, 1, yes, we have, yes, integrating equation 1, then we have fc cosine of nth derivative p, which is equal to, yes, by parts using this identity, this is n minus 1th of this is, yes, clear, f of n minus 1 x cos px, and the limit from 0 to infinity, minus of 0 to infinity differentiating this term, which is equal to, you know that, minus of p, first term this one. So differentiating this is, you get minus of p, yes, here we can say f of n minus 1x, and also differentiating this is minus of p, yes, minus minus plus, this is p of sine px. Yes, okay. Yes. Now we using, as we it is given that this is here, it is given as n minus 1th derivative of f of x vanish as x tends to infinity, and this tends to alpha n minus 1 as x tends to 0. Yes. So using here is, this tends to infinity, then this is 0. If this is 0, then this is alpha n minus 1. And cos 0, you also know, is 1. So this can also be written as, yes, this can be written as minus of, this is infinity, then this is 0. This minus of, this is cos of alpha n minus 1. Then this is minus alpha n minus 1, it is given. Okay. Plus p, okay, p 0 to infinity, this one is, this can be written as sine of term, yes, then this can write it f of s, yes, n minus 1 p. Yes, clear? Fourier transform sine, yes, yes, clear? Now let us, if this is first equation, now if integrating this is third equation, number third, then we, yes, then this equation can be written as fourth equation. Yes, clear? Now this implies that f of c is equal to, now also integrating the equation number 2. Okay, integrating this equation, or solving this equation, you can say. Okay. Yeah, yes, from equation 2, yes, from 2, f s n p is equal to, integrating by parts. Okay. Similarly, you get f n minus 1 x and different and sine px, and limits from 0 to, yes, limits from 0 to infinity, and minus of, yes, p and 0 to infinity f n minus 1 x, and differentiation of sine px, you know, which is cos px, yes. So this is equal to cos px dx. Yes, clear? Similarly, also they are approaching the same steps. F of n minus 1 for infinity, this is vanished, but when turned to 0, then this one, but because of this term sine px, this becomes 0, so everything is 0. Okay, so we get the value is, yes, so you get f of s n p is equal to minus of p, and this can be written as cosine of transform, yes, f of c n minus 1. Okay, I think you have to clear it. Okay, let us suppose that the equation number is 5. Is clear? Okay. Okay. Now eliminating, yes, now eliminating f s 2n minus 1 p from or between 4 and 5, 4 and next one is 6. This one 4 and 5, not in this one equation. Yes, f of s is here, s is here. So eliminating this is okay. In place of you write down this one. Yes, for here you see that f of s is this one. So first step is you have to substitute as n is, you substitute replacing n as n minus 1. Then this become, yes, if you substitute here n as, yes, n as n minus 1, then you get f of s n minus 1 p is equal to minus p, yes, f of c, okay, f of c, and here is n minus 2p. Yes, let us, this equation number is 6. Yes, clear? Now, okay. So eliminating this between 5th and 6th, yes, 5 and 6, we have f of, yes, we have f of c, yes, n is n p is equal to minus alpha n minus 1, and in place of sign you are substituting, then you get minus of p square f of c n minus 2p. Yes, clear? Okay, this equation is 7. You see, is clear? Substituting this, yes, this is n minus, substituting in this equation. Yes, so in place of this, so this is p square, yes, and f of n minus 2. Okay, yes, students, clear? Okay. Now, repeating this process, yes, now this one, next term will become this one, okay, so you substituting this term. If you similarly operating this from f of c n minus 2, yes, similarly this can be become, okay, if you operate the definition is similarly f of c n minus 2 p, yes, this become 0 to infinity f of n minus 2, yes, x cos px dx, yes, and similarly if you are integrating by parts, then you get the next term, you get one, then if first derivative, then f of x, if n, then n minus 1, then so here is f of n minus 3, yes, and here is again of sine of px, sorry, cos of px, yes, cos of px, limit from 0 to infinity, and minus of, here is again minus of p plus 0 to infinity f of n minus 3 x and sine of px. Differentiating cos px, you get minus, so minus plus, which is this px dx. Yes, here you see that in this term, in equation number 7, if you solve this term, then again you get this one. This is also for n minus infinity, this one is for 0, you get alpha of n minus 1, so on. Yes, so repeating this process, you get next another one is p f of n minus 3, like that. Okay, so repeating here you get, by repeating this process we get, so you say that repeating this one, this, then this one, then other one is this one. So yes, So repeating this process we obtain for odd and even functions. Yes. Repeating this process when the sum is odd or even. Yes. Then we get f of c. Yes. 2n. Yes, you say repeating. Yes. Repeating the process. Okay. Okay. We get fc. This is fc p. This one. This term. Okay. This term is equal to minus sigma r is 0 to n minus 1 minus 1 to the power r alpha 2n minus 2r, yes, minus 1 p to the power 2r plus minus 1 to the power n p 2n f of c p. Next, then you get this one term. Okay, and for even and odd term we get, yes, similarly we get next term, which is f of c 2n plus 1 p, which is equal to, we get minus of sigma r varying from 0 to n minus 1 to the power r alpha 2n minus 2r p to r plus minus 1 to the power n p to the power 2n plus 1 f of s, yes, p. Okay, you know the odd or even functions for the Fourier transform. So if you converting this, you get this term for odd term, and similarly for sine term. Yes, sine term here for odd or even functions, you know these properties, so you get this one. Okay, I think you have cleared this step. Okay, now for the next property. Okay, so you have the first property that is the proof of, yes, this. You get first one and similarly the second one. Similarly this property, yes, similarly this property, if you sine, and if you the same process, you start from the sine cosine term, and similarly you start from the sine term. Okay, similarly you get the same process. Okay, students. Now, yes, now, okay, now replacing, yes, now replacing n by n minus 1 in equation number 4. Here is form, here up to 6 in equation number 1. Here you see, here is in equation number 4. Yes, so you get this. We have f of c n minus 1 p is equal to minus of alpha n minus 2, similarly on the same way as you have write earlier. Okay, plus p times f of s n minus 2 p. Okay, now on eliminating, yes, eliminating, yes, fc n minus 1 p between between fifth and equation number, let us suppose that the equation number 8 is this one and 8. Okay, so we get fs np is equal to minus of p. Here is, and here become minus of alpha n minus 2, yes, plus p f of s n minus 2, yes, p. Okay, so this implies that f of s n p, which is equal to p alpha n minus 2. Okay, and minus, this is minus of p square f of s n minus 2 p. Okay, similarly the same thing, repeating the process as you have earlier you have proved. Similarly repeating this process, yes, repeating the process, we get, yes, similarly for the odd even terms, yes, we get f of s 2n p is equal to minus sigma r is equal to 1 to n minus 1 to the power r alpha 2n minus 2r p to the power 2r minus 1 plus minus 1 to the power n plus 1 p to the power 2n f of s p, and also for the odd f of s 2n plus 1 p, yes, which is equal to minus sigma r varying from 1 to n minus 1 to the power r alpha 2n minus 2r plus 1 p r, yes, 2r minus 1